Here we are. So the second one is it's about Kubervisor. So we'll see why it's called like this at the very end, in fact, and it's about pod anomaly detection and system stability. So we're gonna run this presentation together with Cedric. I'm gonna do the presentation, and the brave guy here will run the live demo. So I think you know us now. So as this is a public talk, this is what we are showing few figures about Amadeus. So for the people in Sophia that don't work in Amadeus, here are some figures for our 2016 year. Just one comment on the very last one. You see 600,000 queries per second at peak time. This is what we have overall. I mean, all the query that comes from out of the system, and also the queries that we have inside, because we're running a big distributed system. And when you get one query coming from the outside, this generates somehow 7 more queries inside. This is an average value. Huh? So the agenda, first to go quickly about distributed system and stability. Then we will present the solution that we already have in the platform to improve the reliability of the system. And finally, we go to the Kubervisor project. So let's go. When we have such distributed system, here is just a dummy example. When you have client connecting to services, just imagine that each bubble is a services and that can connect to another one. This is typically what you have when you run microservices architecture. You can have what I would call a butterfly effect in that system, meaning that one small butterfly here in the bottom, whatever small it is, can impact most of your system. Okay, so what we're gonna try to achieve is to prevent this butterfly to propagate to the rest of the system, and this I come back to this in a minute. But just understand that this small error here in the bottom right is even worse when you have many instances of your service, that you have load balancing happening, and more than that, when you have parallel calls being done by one system to another one. This is what I try to represent here. I hope it's clear for everyone. You have two services, A and B, and the service A is going to call the service B. So when everything is fine, it's okay. We're on the left part of the slide. If we have one B instance out of 4 that is failing, if we have round robin and we make only one call from A to B, suddenly your clients that access the A layer is going to have something like 25% failure rate on the queries. Okay? And just imagine that now each A instance is triggering to complete its work 4 calls to the B layer. Okay? I need to call 4 times the availability system to be able to replace and give a good price for a plane. If you have these 4 parallel calls plus round robin, that means that each time the B1 instance that is failing is going to be touched by the system. So somehow you're going to achieve a 100 failure rate for your client in this situation. Okay? So the small butterfly, 1 out of 4, trigger full outage on your system. It's distributed system. Failure is the norm, and so on and so on. We have many quotes in the industry to say that many bad things could happen. Today I would just bring you one other quote about this butterfly effect and chaos theory. Just one famous French artist, Paul Cézanne, we live in a rainbow of chaos. Let's try to keep the rainbow and remove the chaos with solutions. So, talking about solutions. Let's see what the platform already proposed today to us. Yeah. So, what I've said just before is that if we have client talking to a service, himself talking to a B service, if I have this kind of representation, three instances for A and 6 for B, if we have a sequential call 1, 1, 1, we have in the end 1 out of 6 as a failure rate if only one B instance is being failing. Okay. My assumption is that we are doing round robin everywhere for load balancing. Okay. Now, if the A instance needs to make 6 parallel calls to the rest of the system, so the failure rate is 1 on the left. We've seen it in the previous example. Now you have solution if you manage to do proximity-based load balancing. If you're able to shard your system somehow and contain child transaction to this shard of the system, you are going to able to reduce the impact of a failure. So let's take the example of availability zones that are usually one sharding at IaaS level. If you manage to have this proximity load balancing, for example, the B1 instance will be located in one of the availability zones, and only the request that hit the A1 instance here will be affected. Okay? So you're able to serve the same type of traffic in terms of volumes, but with the same constraint, you have clearly reduced your failure rate to 1 out of 3. Okay? Not only that, but it will be easier for you to find the root cause of the problem, because you know where it's located, because here we are speaking about AZ, availability zone. So if it's a problem with a disk, a memory, and so on, you know where the problem comes from. To deal with proximity-based load balancing, there are already 2 issues open in Kubernetes. The first one is trying to collocate calls to the same node. Okay, this is the first reference that I give here. There's another one that is really trying to achieve what I've presented before, being topology aware. And there is even a proposal for that one that's not been merged. I don't know if this is going to be continuing or going forward. But there are other solutions, not natively in Kubernetes, but if you run a service mesh, and especially the one called Istio, this one will put in front of all of your workloads some proxy, and this proxy that are based on Envoy. Envoy is a C++ proxy developed by Lyft company. This proxy is availability zone aware. So by default, if you know that correctly tagged with the availability zone, the proxy will be able to deal with that and route the traffic to the same availability zone. So there are already solutions for doing this proximity-based load balancing. Another option to increase the reliability of the system, if you have some code that don't behave well in terms of memory consumption, for example, and you don't want to go under OOM kill, you can define limits on your pod definition. And as soon as your workload is exceeding this limit, Kubernetes will, and especially the kubelet on each node that is monitoring the container, will kill the pod, not the pod, but the container that is exceeding this limit. So somehow, if you don't manage to fix your bug that is triggering memory leak, this is going to protect you in the end, but try to fix the bug. Probably one of the most famous health check in Kubes, probes. So there are 2 types of probes, liveness probe and readiness probe. These 2 have different purposes, don't mix them. The first one will kill the container if the probe is not okay. The second one will let the container run, but will remove the pod associated to the container from the service discovery. So no more traffic will hit this pod and this container. If you have multiple containers inside the pod, if only one of the probes of one container fail, in terms of readiness, the full pod is removed. No container is going to receive traffic. So the probes are active health check. Active means that we are doing things on purpose to check the health, and this the thing is done by the kubelet. The kubelet is sending probes to each container when the probe is defined. You have 3 ways, technical ways of defining a probe, whatever it is, liveness or readiness. You can work at TCP socket level, checking that a socket can be open. You can do HTTP GET. 200 will be an OK. Anything else will be considered as non-NFI. And finally, you can execute a script, okay, of your choice. You have many parameters to tune the probe. For example, you can initial delay, don't check any liveness or whatever for 30 seconds, for example. And then when the pod is set to be non-healthy, you can set threshold to say how many valid probe you should receive before turning it healthy or non-healthy again. So values that you can customize here. This is all in the pod definition. So one advice or a couple of advice about probes. Keep them simple. Really keep them simple, because what we want to achieve is stability of the system. If you introduce complexity, you may introduce bug. And if you do bugs, this is what's going to happen. One bug in the system in a probe could trigger a complete collective suicide of all your containers. This is service outage for sure. Okay? So try to be simple, and this is one way of avoiding bugs. Don't try to check external dependency chain on your pods and containers. When I say external, I mean external to the pod, of course. First reason, we are running big distributed systems, and somehow, and this will happen if you have multiple services, you will have cycles. Why you will have cycles? Because you're running probably a couple of containers in your services, and one container calling this service, the other one calling the other way around, and so on. And in the end, what's going to happen is that if you need to restart everything from scratch, you won't have any instance ready, so you will never be able to start your cycle, and you will never be able to boot your system again. The second other thing on the bottom right here is that if you're checking the complete chain, it may happen that, for example, the pod A, if you check the dependency B and C, if C is failing, okay, all the service that goes through AC, okay, we don't want them, it's going to fail. But everything that would have gone through AB, now it's not working anymore. Just because you're checking C, which make an A invalid, and so AB invalid. So try not to do that. Keep it simple and scope to your pod. One more solution to increase reliability, circuit breaking. So there is the pattern here on the right. So circuit breaking is what? You notice that one of your dependencies is failing, one of the instances in your dependency pool is failing, and you temporarily remove this instance, re-inject it to check, is it okay or not, reintroduce or not. Okay? I come back to this because Kubervisor somehow does the same thing. How do you achieve circuit breaker? But you can also do it if you have a service mesh that have a proxy that implements circuit breaker. So today on the platform you can install either Linkerd or Istio, and the two of them have circuit breaking feature. Okay, they are not configured exactly the same way, but what's happening is that now all the instances of B are hidden behind this proxy, and this proxy could decide to not going anymore to the B instance, meaning that the load balancing is not achieved anymore by the service discovery or kube, not the kube proxy and so on. You have this proxy in the middle that check all the response of all instances, and if one of the instances is replying control message, error message all the time, the proxy may decide not to go there anymore, implementing this pattern of circuit breaker. If you have this proxy, also they can achieve what we call retry. Retry is that instead of not going anymore to this instance, when an instance is failing, is trying another one. Of course, you cannot do that for all services, but there are some services that you can retry. In that case, you can configure it, and it's easy. So first time the transaction failed, the proxy will choose another instance and try to get a valid value. You can define usually in the configuration how many times you want to retry, not to have an endless retrying loop somehow. Just as an example, here is a dashboard from Istio, and here you can see that you have 4 operations per second for 2 instances, and at that point in time, I was, what is this? Yeah, you have the green is the OK, the blue is the KO, and when I activate retry, everything goes to OK, of course, because everything goes to B2. But at the same time, what you can see is that in terms of number of operation overall count on B, you are almost doubling because it goes to B and B2, B and B1 and B2, and so on, so on, so on. all these nice things that we have seen, they have a couple of limitations, I would say. The first one is that anytime the decisions are taken locally, if you think about the probe is done locally to a container. Each probe does not know what's happening outside. You can try to build some logic to know what's happening outside, but remember, keep it simple. So you don't want to go there, definitively. The service mesh, it's taking decision at proxy level. And proxy, you have as many proxy as you have pods in the service mesh. So again, it's not checking overall what's happening. It's not communicating. All the signals that are used by these layers are kind of technical. With the probes, if you think about a script, you can say, oh, I'm going to look at my file system or dial with my server to check what is the functional stuff and so on. But again, you are entering the complexity part and you take risk doing that. So usually we check against memory. We saw it with pod termination, connection with probe, response time, with the circuit breaking stuff, return call also. And more than that, if you use circuit breaker, your circuit breaker will have to know or understand the protocol that you are using. So fine if you're using HTTP, if you're not, but today you just can't do anything, okay? And at Amadeus, clearly we have our homegrown protocol, and this is not helping us at all. One of the reasons why we have built Kubervisor also. So let's go and discuss this Kubervisor pod anomaly detector that we have created. This is going to be open source soon, okay? Available on GitHub, and I hope you'll get there and try to contribute or at least test it. So what we try to bring compared to the rest is trying to have a kind of orchestrated, more than global, but orchestrated decision, trying to see what's happening overall for a service. We are not looking anymore at a pod or a container, but we are looking globally at the service level. And of course, when we're going to cut some part of the system, now that we try to have a global view, we are trying also not to make the things worse. Okay? If everybody is failing at the same rate, there's no point in cutting one or two of them. We let everyone behaving half-half. And also, we open the opportunity to take decision based on anything else that you have in your system, not only technical indicators that you have at protocol level or so on. And for that, we are going to take advantage of anything that is running in your system that is monitoring your system. This includes business part, okay? And we're going to see how to plug that. And as an example, we are going to use Prometheus today. The Kubervisor is a controller, okay? It's divided in two parts. Remember the circuit breaker pattern? You are closing some connection, reopening, half opening, and that kind of stuff. This is what the breaker and the activator are doing. One is removing, opening the circuit, and the other one is closing the circuit, okay? And we do that with different strategy at breaker and activator level. For the activator part, for example, the three strategies are periodic. So periodically you re-inject the failing instance to see if it's now healthy, periodically. We have what we call the retry and kill. So you will retry periodically, but for a given number of time. After this time, you simply kill the pod. And the last one is what we call retry and pause. You retry 1 time, 2 times, 3 times, and you pause. What pause means is that you don't kill the instance, but you remove it from the traffic for investigation. So it's still there. It's still counted by the replication controller as a one instance, but does not receive any traffic. Okay? These are the three strategies for the activator. For the breaker, we have defined 3 also for the moment, and it can really be extended. One is checking again against discrete value. What are the good values that are returned by your monitoring system and the bad values, and count the ratio of good versus bad values. One is for continuous value, checking the deviation compared to the whatever you want. Could be the maximum, could be the minimum, could be the average, but you compare something. We'll see that in a moment in a PromQL query. And the last one is the custom, meaning that you can plug any external system that will tell you, hey, this pod is not behaving correctly, and you will have all the automation done by the Kubervisor on top of that to re-inject and remove your pod from the traffic. The Kubervisor is built on top of a CRD in terms of definition. So now that you know that what a CRD is, I don't get into this detail. And yeah, here is examples of specification that you can have for the Kubervisor service. So as any resource, it has an API group, a version. It's namespaced, even if we don't see it here. It has a name, of course, and then you have a spec. You say in the spec which service you are monitoring. Then you said how many pod minimum in terms of ratio or count you want to have. This is to avoid full outage and trying to kill everyone. So if you have pod disruption budget apply to your system, this could have to be higher value compared to the pod disruption budget. Okay, pod disruption budget is for Kubernetes not to kill all the pods, for example. But here you can define a threshold a bit higher for the system. Here we have an example for the continuous value deviation. So we would accept 30% deviation, and we say where the Prometheus server is running, and we send the PromQL query that will return a float that is 1 if there is no deviation, and 0.2 if there is 80% deviation, or 1.80 depending on which side your deviation is happening. On the activator side, here we have mode periodic, and we have a period of 15 seconds. Almost the same thing, but different strategy for the breaker. Here we have a discrete value out of the list. So in fact, it should be or. It's either you define good values or bad values, but not the two at the same time. We have to fix this here. And a different strategy in terms of activation. Here we have a retry and pause. Once a pod would have been breaked more than 2 times, it will be moving pause. And last one, I think also I have an example. Yeah, here it's with the custom one. You target an external service that tell you the list of pod. No computation at all inside the Kubervisor controller. So, just before the demo, for you to understand the architecture, we have something very classic, a service, behind the service 4 pods. So the selector is matching all these 4 pods. We have a metric server here that is scrapping metrics, so functional, technical, whatever, that we put in this metric server. We're going to use our preferred one here at Amadeus, it's Prometheus. And we're going to run the controller Kubervisor next to it. Then in terms of interaction with the system, your operator, your DevOps or SRE guy, will have to do 2 things. First, inject the Kubervisor service definition, the one that we have just seen. Okay. Thanks to that, the Kubervisor will understand which service you need to focus on and deduce what are the impacted pods. And it's going to append one label to all these pods. That is Kubervisor traffic equal yes. So for the moment, we have just added one label to all our pods. But if we want the Kubervisor to run completely, we're going to ask our user to also change the selector of the service, saying, now I want everything that is traffic equal yes from a Kubervisor point of view. What this means is also that you can run the full Kubervisor stuff in a kind of dry run mode. If you simply don't put this, Kubervisor is going to report many things in terms of what is breaked or not, but this won't have any effect on the system at all. So you can really try to understand what's happening before really activating it at scale. So what's happening when a pod is failing? The Kubervisor will notice the deviation thanks to the anomaly detection strategy that is applied, turn the traffic label to no, and of course the selector does not apply anymore, so this pod won't receive any traffic for the service. So, demo time, Cedric.
So like for any demo, I hope it will work, because sometimes demo didn't work. So like we say in the introduction, so Amadeus is working with the travel industry, and so for the demo we created a dummy flight price search that is returning the 3 best price for an origin and destination city on the current day. If we took the previous slide, what is looking very similar that we saw before is that we have a service pricer, and behind we have 4 pods running. We will create several Kubervisor services with different configuration in order to see the difference between periodic, retry, and pause, and so. And that's it. So let's go to the demo. So for that, no, thank you for the light. So let's see first what is already running inside my Kubernetes cluster. So I use Minikube for that. It's, I don't rely on Wi-Fi. It's already a good reason to not have issue during the demo. So I have 4 pods, like I said, for my processor. I have also Prometheus running, and I use a Prometheus operator to operate my Prometheus cluster. So very standard things. Here on the top of the screen, I can see I do a watch on only my application, so I do a label selection equal pricer, so I see my 4 pods and the service associated to it. If I go back here, what I can see, I have my Prometheus cluster here. So if we want to run something, we will see it. And we also created a Grafana dashboard that we will see the price per pod and also the number of requests on each pod. And my service, in fact, is here. So if I run it, what I receive 3 price with here the queries Paris, London. I have the date, the price, and so. So to generate some traffic, I have an injector here on the right. So you can see that all the prices look quite similar. It's between 700 and 1,100, I think. This is a random value, but depending of the distance. So this is not the official price. So let's start. So I already have everything running. So I will create the first configuration for my Kubervisor service is here. So you can see the breaker. It's I want at least to have 2 pods running or 50% ratio running. I can see here my promql query. So if I copy here and go to promql here, I should see something. Yeah. So here I can see that I have traffic, or I have value at least for each pod, for the 4 pods. Coming here, just need to refresh maybe, or to wait a bit. Let's reload it. So demo effect already. Why?
Your time shift.
Yeah, it's because my
Yeah.
I do a okay. So before my office and here I stop my computer, so the time of my VM and my computer is not the same, so it's a bit let's do like
Shifted in time.
yeah, have a shift time. Let's continue. It will not impact more the demo, I think. So here, so breaker information here, and the activator, so periodic one. So currently all the prices are still okay. I didn't inject any anomaly inside any container. So first so this was a cat, so now let's apply the Kubervisor services. So I don't know if you saw it, but we have no new labels on my pods. I have the name here of the Kubervisor services, so pricer 1A, and the label like we saw before, traffic equal yes. So now let's put some anomaly in 1 pod. Okay, just before that, I updated the services to add in the label selector the traffic equal yes. And now I think it's a time to generate some anomaly in 1 pod. So I select randomly 1 pod between the 4 pricer pod. And as you can see, I configure it that now 1 pod is returning 0 as price. So it's very good for our clients, but not for us. So we want to limit this. So yeah, so I created a services in my pod where I can tune the configuration, and so I can define a price €0 per kilometer. And so what you can see here, one pod with the problem have no traffic equal no, and now we don't have any more zero happening. So after 15 seconds, the activator will put inside behind the services the pods, and we saw new zero happening, new null value, and again he will remove it automatically, and this he will do it. This he will do it all the time because we choose a periodic, so he will retry every 15 seconds to put it back inside the traffic. So this is not really that we want for our user, so we still have the issue. So let's try another strategy. So we will use activator, retry and pause. So what you can see here before that is that inside the CRD, we update the status of the activity attached to this Kubervisor services. So here you can see that we have the 4 pod managed, and when I do the get of these resources, it was yes, so I don't see any pods stop or not. And this is so if you want to interact with the Kubervisor, you will interact with the CRD, looking at the status here to know what's happened on your for your system. Yeah. Go.
I was just going to add that here we are using the continuous value deviation. So we accept 30% deviation on the average price. This is what the big PromQL is doing here. It's comparing the average of each pod compared to the average of everyone. Okay, so it's not because we have 0, it's because we have a deviation that is more than 30%. So would it be 10 or 20, we would have the same effect. Okay.
Yeah. Just before so I deleted the pod with anomaly, and what we can see here before is that one pod started to receive less traffic because we cut it several times, and the other one take more traffic because since you have only 3 pods and not 4, the other one take more traffic, and this is the price. So we saw the anomaly here that the price go to 0 for 1 pod. And this is due to this difference that we have a deviation, as explained by David. So now we will change the configuration. Like I said, we will retry and pause. So let's apply this update on the Kubervisor services. We will modify the configuration of another pods to create again some bad behavior of one pod. So we can see that now another pod start to return a null value for the price. Unlike before, we should see that the traffic will go to no for one pods when the anomaly will be detected.
So it takes a bit of time to start to know because we are making an average of 1 minute. This is what you see on the PromQL query here. So in the PromQL query, you have several things that you can parameter. Here, for example, is the time window on which you do the computation. And you can see a end delta price count on 1 minute more than 3. This means that this system will react only in case you have at least 3 requests over a minute. Under this threshold, nothing will happen for this pod.
So we saw that the traffic now is equal to no. It already happened once or maybe 2. So to know how many times the Kubervisor try to put back the pods inside behind the services, what we do, we don't add another label, but we add a notation that we can see here. I just need to take the name of the pod that so 8S, so this one. And here what I can see is that my breaker tries 3 times to break it. So that's why it's more than 2, and so the activator don't try to put back the pods behind the services.
And you have the pause. You can show the pause.
Yeah, and here it's not traffic equal no or yes, it's traffic equal pause. So it means that the breaker understands that he will the activator will not try to do anything else. A good thing also to put it in annotation is that all the information is not stored in the memory of the Kubervisor controller. So if we restart the controller, everything will be reconfigured automatically, and we don't have any state inside the Kubervisor controller. And in the statue, like before of the CRD, what we see that we are still 4 pods managed behind these Kubervisor services, and we have 1 pods in pause. So let's change again the configuration of the Kubervisor services. So I remove the pod with the anomaly. Change the configuration. So this time I will apply retry and kill. So instead of putting pause on the pod that is have anomaly, after 2 retry, so at the third time, it will kill the pod, and like this, Kubernetes will recreate a pod replacing the missing one. So let's apply the configuration. Again, create some anomaly in 1 pod. So we can see some price are wrong. Yeah. So this was the first pod with anomaly, and we can see here the last retry. So normally now it should be detected also. So traffic equal no. If we take the name L9 in, let's go back here, this one. So for the moment it's only try once. 2. So come back here. So what we should see in the next iteration is that instead of putting in pause the label, we will see terminating on this pod, and a new one will be created. So we can be more aggressive on the period, but since we don't inject too much traffic, so we need we choose 1 minute to detect issue. But if we have more traffic like here, it's only 10 queries a second, I think. We can reduce test it in 15 seconds if we want it.
Yeah, and the retry period is kind of exponential, meaning that the first time it's cut for 15 seconds, the second time for 30 seconds, and if you go more and more, it's multiplied each time.
Okay, we didn't saw it, but it's already restarted. Yeah. So we can see that the pod that it was starting by L9 it was removed, and a new one is running. So everything now it's all the prices are okay. So let's do another thing. So now I will inject error on all pods. So all the values are wrong. So what you can see here is that currently, since all the pods are in failure, the Kubervisor will not try to kill all the pods in order to avoid the fact that we have a service outage. And so, well, okay, we
should have some no flashing, but
yeah, so we need to wait a bit.
But you don't have any deviation now from one.
Yeah,
but you have on the first time window, floating time window, you have in fact.
Yeah, we should.
Because all the previous pods were returning something like 1,000, and suddenly everyone is returning 0. So compared to the global average over a minute, you have some problems. So at the beginning, you should see, maybe we haven't seen, but it must have been very fast. 2 of them must have gone to no. And it's true that at some point, the floating window is moving toward everyone is at 0, and you have no more anomaly because no more deviation. But at the when you switch completely to everything to 0, we should have seen some kind of, let's say, false positive.
So yeah, so maybe next time I will do it only on 3 nodes to have the deviation, but maybe it will remove the wrong one. So it's not a good things to do. So that's it for the demo. I hope it was fine for you and understandable. Let's continue. We have still some slides. So let's talk a bit about how it is implemented. So as any controller, we rely on a CRD. In this CRD, as you saw, we have the configuration of the breaker and the activator, and the controller is watching, thanks to the informer pattern that is proposed by Kubernetes, to watch any activity on this CRD. The controller also watch activity on pods and services in order to add annotation and to watch the value of labels also. And then, as explained by David before, is that we have the controller is separated after in 2 parts, the activator and the breaker part. We have a proper interface to plug any anomaly detector interface. So the only method that you need to implement behind is the get pod output of bounds, and in fact you receive a list of pods with the value associated to each pods. So thanks to this architecture, we was able to plug easily one solution for metrics, that is Prometheus, and put the promptual configuration inside the Kubervisor services. With this architecture, you can modify it a bit to add your own system, or use, like we saw, the custom solution to plug your anomaly, your metrics input.
If you want an example of what you can do as custom, on the repository, the unit test and the end-to-end test are plugging a custom strategy behind. So this is something that probably can be extended. I hope people will have many ideas around that. One that we have already is Kubervisor is doing its job and putting some labels on the pods. We're not using these labels in another context. I've been working with some of the guys here who are working on canary deployment. And why not having a canary deployment strategy that is looking at these labels and check that is my canary healthy or not, just based on the Kubervisor traffic label, sorry. So this is one possible extension. I'm pretty sure that we can imagine many things. So the key takeaway for this presentation, we have many things to in Kubernetes already, probes, and thanks to circuit breaker, we can increase the reliability of the service. This solution extend this toolkit, I would say, and give you some opportunity to work on functional metrics, trying to orchestrate a bit what's happening at cluster level for health checks. We have based all our stuff on standard things that you find in Kubernetes, trying to work on top of service. Our object definition is done on top of CRD. We have used Prometheus that is really heavy used inside this ecosystem. It's extendable. You can plug whatever strategy that you want inside the code, but not only inside the code. If you think about it, just by changing the PromQL that you have seen, you can do many stuff. We have just worked on deviation on top of the average value of a price. Whatever your business, I'm pretty sure you can think about any other query. If you are already monitoring your system, you're going to have tons of idea of what kind of PromQL you can put here. You can even think about trends. Is my value compared to last week or previous hour? You can do many things here. So I hope you enjoyed the presentation. If you did, it's open source, so really we'll be happy to get your your feedback with issues. Try it, break it, contact us, and tell us if it makes sense for you. So some reference to grab the code and the demo that was run by Cedric. So already you answer one question in that slide. If you don't understand the name of this product, here is the reason why. And now we can take any question.
Yeah, just a question about the scalability of this mechanism. So here you execute a lot of PromQL queries. So what about the pressure you put on the Prometheus layer?
No more than the alerting one, and also you can define the frequency of this. So it's true that it's more query on your monitoring system. You have to deal with it if you want to get the benefit of it. But you can really put some parameter. You can run, as you know, multiple Prometheus instance. If you want to have your metrics dedicated to Kubervisor in one dedicated server and don't put pressure on your, let's say, company Prometheus, you can also. Because in the Kubervisor, you just say, I'm going to use this instance of Prometheus. So you can have a dedicated instance for your application, for a service even. So there are many ways to deal with the scalability of the solution, I would say.
I have a question regarding Kubervisor and the combination, for example, with the readiness probe. According to you, would it make sense to combine those kinds of monitoring system? Or
yes, definitively yes. You're not going to check the same things. If there is something that you can do with probe, because it's simple, and something that you need to do locally, just do it this way. Okay. If you need more complexity in terms of logic, doing average, comparing with other stuff, maybe use Kubervisor. But for example, if you want to check that you have a connection to a DB, because if you don't have it, you simply don't serve, Kubervisor is not going to help here. Really use probe.
And my concern was, for example, if your circuit breaker decides to put back a node that is in readiness no.
This is complementary. Yeah, because the readiness probe does not work with the selector. It takes all the pods that are on the selector, and then depending on the result of the prod, it puts the endpoint in a different section in the endpoint object. So if you open an endpoint object, you will see ready endpoints and non-ready endpoints. Okay, this is what the probe does. Kubervisor even remove the pod from the service discovery. So it's not appearing anymore, not in the ready nor in the not ready.
So do you think that this can be adapted to do auto-scaling, but using Prometheus metrics, a kind of a supervisor for this? Imagine the situation where I have the resources on like a full 100% or 99, doesn't matter, but I'm really cheap. I don't want to have another pod running. But if I have a queue, for example, of availability requests incoming, and I want to reply then in 3 seconds, so and based on a prompt QR, I know that, and then I scale one pod more to.
So for that, Kubernetes already offers the possibility to provide custom metrics for the autoscaler pods. And you can use Prometheus. So you need to have a converter a bit, but it already exists. You have some example already in internet that people is using Prometheus metrics to have this kind business or other stuff like the response time that is not taken into account currently with the default autoscaler.
I'm wondering if you don't have false positive because there was a 15 seconds to wait for retrying to restart failing pod, but the average was on 1 minute. So I'm wondering if, depending on your ratio, you could have the time before the 15 seconds where it was failing, that make it fail even if it's now working fine. You see what I mean? Or you have to tweak the figures precisely between the ratios, the PromQL and the period.
Completely, yeah. You can have this kind of stuff. So, and especially if we deal with average stuff, if you have low number of pods, the overall average is really affected by the fact that one pod is failing. So yes, this is all about statistic on floating time windows here. So you could have some side effects at the border of the windows, or just like the one you have described. But I would say that this should converge at some point. Maybe you will find some pattern where it's kind of periodically failing. Maybe I'm not sure, but that's possible.
It might put it down once, but then after 30 seconds it will.
Maybe we can take question on the WebEx if there are any. So silence on the WebEx. So we are at the end of this presentation. I hope you enjoy it. And you will have to wait a bit for the open source. It should come next 2 or 3 weeks if you want to play with it. And if you have other questions after this session, just send question on the comments in the Meetup website, or for the people internally in Amadeus, you can just contact us. And thank you for attending.
Thank you.